Physics just broke, and nobody's talking about it. On October 18th, 2025, an image processed from August observations captured something that shouldn't exist. The Keck II Observatory, perched on Mauna Kea in Hawaii, had been tracking Comet 3 Atlas for months. What they revealed in their October analysis wasn't just unusual, it was impossible. Material streaming toward the sun, not away from it. Toward it, like watching a river flow uphill. Like seeing smoke descend into a chimney. The entire foundation of cometary physics, built over centuries of observation, suddenly felt uncertain. Picture this in your mind. Every comet you've ever seen in a photograph, every textbook illustration, every artistic rendering follows one unbreakable rule. The tail points away from the sun. Radiation pressure from our star pushes dust and gas outward, creating those magnificent sweeping tails that grace our night skies. Solar wind, that relentless stream of charged particles flowing from the sun's corona, acts like an invisible hand shoving material into the darkness of space. This isn't speculation, this is fundamental physics, confirmed by thousands of observations across 4 centuries of astronomy. When Edmund Halley predicted his comet's return in 1758, when NASA's Deep Impact probes smashed into Tempel 1 in 2005, when Rosetta orbited 67P for 2 years, every single observation reinforced this truth. Tails point away from the sun. Always, until August 2nd and 3rd, 2025, when Keck II's adaptive optics system captured something different. The images weren't released immediately. That's crucial to understand. Raw astronomical data requires extensive processing. Artifacts must be eliminated. Instrumental effects must be accounted for. When dealing with objects millions of kilometers away, every pixel matters. The processing team worked through August, through September, checking and rechecking their analysis. By October 18th, they were certain enough to go public. What they revealed was an anti-solar tail, a jet of material streaming from 3I Atlas's nucleus directly toward the sun, visible across multiple wavelengths, confirmed by independent analysis. The structure appeared in both the visible spectrum and near-infrared imaging. This detail matters because it eliminates one immediate skeptical response. Maybe it's just a reflection, an optical illusion, a processing artifact. But artifacts don't show up consistently across different wavelengths. Illusions don't maintain structural integrity through independent verification. What Keck II captured was real material, actual substance ejected from the comet's nucleus, traveling in the wrong direction. Imagine standing in a hurricane, watching leaves blow toward the storm's center rather than away from it. Imagine opening your freezer and feeling heat pour out. The cognitive dissonance is immediate. Your brain knows this violates basic cause and effect. That's exactly what astronomers felt reviewing these images, except their discomfort wasn't about violated expectations. It was about violated physics. The tail structure extended several thousand kilometers from the nucleus, visible against the background star field, not subtle, not marginal, not something you could dismiss as measurement error. The Keck II team used Laplace filtering techniques to eliminate background contamination, ensuring what they were seeing originated from the comet itself. They cross-referenced their observations with star catalogues, accounting for proper motion, eliminating cosmic rays, removing every possible source of false positives. The result remained unchanged. Material flowing sunward. Now, you might be thinking this is sensationalism, that there must be a simple explanation astronomers haven't yet articulated publicly. That's reasonable skepticism. But here's what makes this different. By October 2025, this wasn't the only observation. Hubble Space Telescope had captured hints of unusual structure in July 2025 observations, though those images weren't initially recognized as anomalous. The Gemini South Observatory in Chile had tracked tail development throughout August and September. Mars orbiters, ExoMars Trace Gas Orbiter and Mars Express, had both imaged 3I Atlas during its closest approach to Mars on October 3, 2025. capturing the comet from a completely different vantage point. Every observation showed consistent anomalies. This is where pattern recognition becomes unavoidable. One unusual observation might be explained away. Two requires attention. Three or more demands explanation. We're well beyond three. The Keck II image specifically showed a narrow collimated jet rather than a broad diffuse tail. This detail is significant. Cometary jets are common, localized areas of outgassing from active regions on the nucleus, but jets typically radiate outward in all directions from active spots, following the pressure gradient of sublimating ice. They don't organize into coherent beams pointing toward the sun. The geometry makes no physical sense under standard models. Radiation pressure should disperse sunward-traveling particles before they could form a visible structure. Yet, there it was, persistent and undeniable. The technical specifications matter here. Keck II's adaptive optics system can resolve structures as small as 0.05 arcseconds, roughly equivalent to spotting a coin from 100 kilometers away. This isn't blurry photography from a backyard telescope. This is cutting-edge imaging that can detect individual asteroids in the main belt, that can resolve details on Pluto's surface using advanced techniques, that regularly contributes to Nobel Prize-winning research. When this instrument shows a structure, that structure exists. What's equally important is what the image didn't show. There was no obvious dust tail in white light observations. Typical comets develop two tails, an ion tail of charged particles blown directly away from the sun by solar wind, and a dust tail of larger particles pushed more gently by radiation pressure, creating a curved structure. 3I Atlas showed neither clearly. Instead, this anomalous sunward feature dominated the appearance, like seeing a car with only a reverse gear. The astronomy community's response has been measured, but unmistakable. Peer-reviewed papers submitted in late October 2025 carefully describe the observations without jumping to exotic explanations. That caution is appropriate. Science advances by explaining observations within existing frameworks before invoking new physics. But read between the lines of those papers. Phrases like unexpected morphology and requires further investigation and challenges current models appear repeatedly. These are the carefully worded acknowledgements that something significant is happening. For viewers who care about evidence, who value seeing through the noise to what's actually real, this image represents a threshold moment. Not because it proves anything definitively, but because it forces questions that can't be dismissed. Why would material travel toward the sun? What mechanism could produce this? Is this related to other anomalies already detected in 3I Atlas's behavior? And perhaps most importantly, if this violates our understanding of cometary physics, what else about this object have we misunderstood? The image from August 2nd and 3rd, processed and released in October, stands as documentary evidence that our models are incomplete. Something is happening with 3 Atlas that our textbooks didn't prepare us for. The question isn't whether something strange is occurring. The data confirms that beyond reasonable doubt. The question is what that strangeness means and whether we're ready to follow the evidence wherever it leads. But before we can answer that, we need to understand how astronomers confirmed this impossible observation across multiple independent platforms, eliminating every possible source of error. The first rule of anomalous astronomy: verify everything twice, then verify again from a different observatory on a different continent using different instruments. When Hubble Space Telescope captured 3I Atlas in July 2025, nobody immediately recognized anything unusual. Hubble observes thousands of objects annually. The data goes into archives, waiting for detailed analysis. Only in retrospect, after the Keck II revelation in October, did researchers return to those July images and notice subtle asymmetries in the coma structure. Features that didn't quite match the expected distribution. Nothing dramatic enough to trigger immediate alerts, but present nonetheless. This is how discovery often works in astronomy. Not sudden revelation, but gradual recognition that something in the data doesn't fit expectations. Hubble's advantage is its position above Earth's atmosphere. eliminating the turbulence and distortion that ground-based telescopes must correct for using adaptive optics. When Hubble shows a structure, you know it's not atmospheric effect. The July observations used Wide-Field Camera 3, capturing both visible and ultraviolet wavelengths. In UV, where fluorescence from molecules like hydroxyl becomes prominent, the coma showed irregular brightness distributions, not the symmetric glow expected from a normal comet releasing material uniformly from a rotating nucleus. Then came Gemini South. Located in Chile, this observatory benefits from some of Earth's clearest skies, where the atmosphere above the Andes provides exceptional viewing conditions. On August 27, 2025, Gemini South began a series of observations tracking three eye atlases developing tail structure. Unlike Hubble's single-pointing observations, Gemini conducted a temporal sequence, capturing the comet over multiple nights. This revealed something crucial. The anomalous feature wasn't static. It evolved, growing more prominent as the comet approached perihelion. The Gemini observations used narrowband filters targeting specific emission lines CN, C2, C3, molecules that fluoresce at characteristic wavelengths when exposed to sunlight. By isolating these emissions, astronomers can map the distribution of specific chemicals in the coma. What they found was asymmetry. The CN emission was stronger on one side, suggesting either a rotating nucleus with active regions or, more intriguingly, directional outgassing that didn't match rotation models. By late September 2025, 3 independent observations from 2 ground-based observatories and 1 space telescope all showed consistent anomalies. But the most dramatic confirmation came from an unexpected source: Mars. On October 3, 2025, Comet 3I Atlas passed within approximately 30 million kilometers of Mars, close enough for spacecraft orbiting the red planet to attempt imaging. The ExoMars Trace Gas Orbiter, a European Space Agency mission designed to study Martian atmospheric chemistry, turned its high-resolution cameras toward the comet. So did Mars Express, ESA's older but still functional orbiter that has circled Mars since 2003. Both spacecraft face a significant challenge. Comets are faint, 50,000 times fainter than typical targets for planetary spacecraft. Imaging requires long exposures, precise pointing, and sophisticated processing to extract signal from noise. But they succeeded, and what they captured corroborated everything the Earth-based observations suggested. From Mars's vantage point, roughly 30 million kilometers away, 3I Atlas appeared as a fuzzy patch against the star field. The spacecraft instruments aren't designed for deep space astrophotography. They're built for photographing Mars's surface from orbit. Adapting them for comet observation required creative use of their capabilities. ExoMars TGO's color and stereo surface imaging system, normally pointed downward at Martian terrain, was aimed outward into space. Mars Express's high-resolution stereo camera, designed to map geological features, was repurposed for astrophotography. The resulting images lack the clarity of Keck II or Hubble. They're grainy, with lower resolution, but they show the same asymmetric structure, the same anomalous feature, confirmed from a completely different geometric perspective, from instruments that have no instrumental biases in common with Earth-based telescopes, using different detectors, different optics, different processing pipelines. This is the gold standard of observational confirmation, independent verification from diverse instruments. Why does this matter so much? Because every telescope has systematic errors. Ground-based instruments deal with atmospheric distortion. Space telescopes have pointing uncertainties. Every detector has hot pixels, read noise, dark current. Every analysis pipeline has assumptions built into its algorithms. When you see something unusual in one observation, your first instinct should be skepticism. Maybe the telescope was slightly out of focus. Maybe the processing introduced artifacts. Maybe cosmic rays hit the detector at an unlucky moment, creating false features. But when multiple telescopes, using different technologies, operated by different teams, processing data with different software, all show the same feature. That's when skepticism transforms into recognition. That's when this might be real becomes this is definitely real. Now we need to understand what it means. The verification process involved extensive artifact elimination. Astronomical images contain multiple sources of contamination. Cosmic rays strike detectors, creating bright spots that must be removed. Background stars appear in the field, requiring subtraction. Light from the telescope structure or nearby bright objects can create scattered light. Satellites pass through the frame, leaving streaks. Every observation requires careful cleaning before analysis can begin. The teams working with Keck II, Hubble, Gemini South, and the Mars orbiters all applied different cleaning techniques appropriate to their specific instruments. They used different star catalogs for background subtraction. They made different assumptions about point spread functions, how a point source spreads across pixels, yet despite these methodological differences, they all arrived at consistent results. The anti-solar feature appeared in every properly processed image. This convergence of evidence is what makes the October 2025 revelation so compelling. It's not one scientist making a bold claim based on marginal data. It's multiple teams, multiple telescopes, multiple observation dates, all confirming that 3i Atlas is doing something comets aren't supposed to do. And here's where the story becomes even stranger, because the anomalous tail structure isn't the only impossible thing about 3i Atlas. While observers were documenting its bizarre morphology, spectroscopists were discovering something equally troubling in its chemical composition, a metal signature that makes no sense for any natural comet we've ever studied. Comets are dirty snowballs. That's the phrase you've probably heard. It's not wrong exactly, but it vastly oversimplifies what comets actually are. They're complex chemical factories, mixtures of water ice, frozen carbon dioxide, carbon monoxide, methane, ammonia, and dust, silicate grains, organic compounds, and trace amounts of metals. When a comet approaches the Sun, these ices sublimate, transitioning directly from solid to gas without passing through liquid phase. This outgassing creates the coma, that fuzzy cloud surrounding the nucleus, and eventually the tails we observe from Earth. Spectroscopy lets us read this chemical composition. When sunlight passes through the coma, molecules absorb specific wavelengths corresponding to their electronic and vibrational states. By measuring which wavelengths are absorbed, we can identify which molecules are present. It's like taking a chemical fingerprint of the comet without ever touching it. For 3i Atlas, spectroscopic observations began as soon as the comet became bright enough to study, which happened around July 2025, as it ventured inside 3 astronomical units from the Sun. Multiple teams conducted observations throughout August, September, and October, using spectrographs attached to major telescopes worldwide. What they found challenged every assumption about cometary composition. Nickel, abundant nickel. Specifically, neutral atomic nickel, visible through its characteristic emission lines at 341.5 nanometers and other wavelengths in the ultraviolet and blue regions of the spectrum. This isn't completely unprecedented. Trace amounts of nickel have been detected in some solar system comets. But the quantity seen in 3i Atlas's coma was extraordinary, and more importantly, the ratio compared to iron was completely wrong. In every solar system comets studied spectroscopically, nickel and iron appear in roughly similar abundances when they appear at all. This makes sense. Nickel and iron are cosmically abundant elements, formed in similar stellar processes, incorporated into forming planetary systems in comparable quantities. When you see iron emission lines from a comet, you expect nickel at roughly similar levels, maybe varying by a factor of 2 or 3 depending on the specific mineralogy of the dust. 3i Atlas showed nickel at levels 8 to 10 times higher than iron, not twice as much, not 3 times, nearly an order of magnitude more abundant. This is the kind of ratio you don't see in natural solar system materials. It's the kind of ratio you see in carefully engineered alloys, in materials designed for specific properties like corrosion resistance or high-temperature performance. It's the ratio found in specialty stainless steels and industrial compounds, not in pristine primitive materials that formed billions of years ago in a circumstellar disk. But wait, it gets stranger. The nickel and iron didn't appear at the same time as the comet approached the Sun. Nickel emission lines became detectable around August 2025, when the comet was approximately 2.64 astronomical units from the Sun. At that distance, surface temperatures on the nucleus would be around 150–180 Kelvin, cold by terrestrial standards, but warm enough to sublimate carbon dioxide ice and begin driving significant activity. The nickel appeared, bright and undeniable, in the spectra. Yet, iron remained essentially absent until the comet moved inside 2.3 astronomical units in late September 2025, corresponding to temperatures above 200 Kelvin. For weeks, observers saw strong nickel emission with no corresponding iron signature. This temporal separation is profoundly strange, because nickel and iron should have similar volatility profiles. They're both refractory metals, meaning they don't easily vaporize. When present as metal grains in dust, they should be released together as the ice binding them sublimates. When present as compounds, their volatility depends on which compounds, but those compounds should incorporate both elements similarly. The most sophisticated explanation proposed involves metal carbonyls compounds where nickel or iron atoms bond with carbon monoxide molecules. Nickel carbonyl, NiCeCO, is volatile enough to sublimate at relatively low temperatures, potentially explaining early nickel release. Iron pentacarbonyl, Fe, is somewhat less volatile, potentially explaining delayed iron appearance. This chemistry exists in industrial processes here on Earth, where nickel carbonyl is actually produced and used in nickel refining. But here's the problem with the carbonyl hypothesis. It requires very specific formation conditions. Metal carbonyls form when metallic particles are exposed to carbon monoxide at particular temperatures and pressures. In Earth's industrial processes, this happens in controlled reactors. In space, you'd need an environment where fine metallic nickel or iron particles coexist with abundant carbon monoxide at temperatures where carbonyl formation is favored, probably somewhere in the 50–100 Kelvin range, where the resulting carbonyls remain stable until the comet approaches the Sun billions of years later. Could this happen naturally? Possibly. Molecular clouds contain carbon monoxide. If 3I Atlas formed in an unusual region of its home star system, if its parent body experienced specific heating events, if multiple unlikely factors aligned, then maybe metal carbonyls could form and survive. But this requires stacking hypothetical conditions to explain observed data, and in science, when you need multiple special conditions to make your explanation work, you should start questioning whether the explanation is actually correct. Adding to the puzzle is the detection of hydrogen cyanide at 2.13 astronomical units from the Sun in early October 2025. HCN is a common cometary molecule, so its presence isn't surprising. What's notable is the abundance ratio. The CN emission from photodissociation of HCN by sunlight was stronger relative to water emission than typical solar system comets show. Combined with the metal anomalies, this suggests unusual chemistry throughout the comet's composition, not just in one component. Spectroscopy also revealed carbon monoxide emission, unsurprising for a comet but worth noting. Co-sublimits at very low temperatures, well below water ice. Its presence indicates the comet contains volatile ices beyond just water, consistent with formation in the cold outer regions of a planetary system. But again, the relative abundances seemed off. More carbon monoxide relative to water than most solar system comets show. You're starting to see a pattern here. Every chemical measurement of 3I Atlas reveals ratios that don't quite match our experience. Not wildly different, not utterly alien, just off, consistently off. the nickel-to-iron ratio is wrong. The CN-to-water ratio is unusual. The carbon dioxide abundance, which we'll explore shortly, is extraordinary. Each individual measurement might be explainable through some specific formation environment, but taken together, they paint a picture of an object with chemistry that doesn't fit our standard models. Think about what this means. Comets are supposed to be pristine samples of the material from which planetary systems form. They're leftover construction material, frozen time capsules preserving the chemistry of their birth environment. When we study a comet's composition, we're reading the chemical fingerprint of whatever star system created it. 3I Atlas's fingerprint is peculiar. It speaks of formation conditions that don't match any environment we've studied in our own solar system. Or, and this is the possibility that hangs unspoken in the technical papers, it speaks of processes that aren't natural at all, processes that involved selection, refinement, design, the kind of nickel-to-iron ratio you'd choose if you wanted specific material properties, the kind of compound chemistry that suggests deliberate engineering rather than random accretion. I'm not claiming that's the answer. I'm pointing out that natural explanations for 3I Atlas's chemistry require increasingly exotic scenarios, and at some point, we have to acknowledge that exotic natural process and artificial intervention become competing hypotheses that both require evidence to distinguish. The data we have now doesn't definitively favor either, but it does definitively rule out normal comet from a normal star system. The nickel paradox is just one piece of this puzzle, but it's a piece that doesn't fit anywhere in the picture we thought we were assembling, and when combined with what James Webb Space Telescope discovered about the comet's volatile composition, the picture becomes even more perplexing, revealing chemistry that suggests this visitor formed in an environment profoundly different from anything in our solar system's history. Water defines comets. That's been the working assumption since the 1950s when Fred Whipple proposed the dirty snowball model. Water ice dominates cometary composition, with other materials mixed in as minor components. When you think of a comet, you're thinking of a nucleus primarily composed of water ice, released as vapor when the comet approaches the sun, creating that characteristic coma and contributing to those magnificent tails. 3I Atlas didn't get the memo. In September 2025, James Webb Space Telescope turned its infrared instruments toward the comet, capturing spectra in wavelength ranges inaccessible to ground-based observatories. JWST's capabilities are extraordinary. It can detect molecules by their absorption and emission in the infrared, where vibrational and rotational transitions provide detailed chemical information. What JWST revealed rewrote our understanding of what an interstellar comet's composition could be. Carbon dioxide dominated the spectrum, not water vapor. Carbon dioxide, in a ratio of approximately 8 parts CO2, 1 part water. This is backwards. Completely backwards. In typical solar system comets, water outnumbers carbon dioxide by factors of 10 to 100. Water is the primary volatile. Everything else is secondary, but 3I Atlas reversed that relationship, showing more carbon dioxide than water by a significant margin. Let's ground this in something concrete. Imagine finding an iceberg floating in the ocean, but when you analyze it, you discover it's mostly frozen carbon dioxide with just a little water ice mixed in. That's not an iceberg as we understand the term. That's something fundamentally different, something that formed under completely different conditions than any iceberg Earth's climate has ever produced. That's 3I Atlas. Carbon dioxide ice exists in our solar system. Mars's polar caps contain significant CO high Vi. Comets contain some CO high Vi, but as the primary component, that requires formation in an environment much colder than the regions where water ice dominates, or formation from molecular cloud material with unusual chemistry or parent body processing that preferentially retains CO foul while losing water. None of these explanations is simple. Formation temperature matters here. Water ice condenses from solar nebula gas at temperatures around 150–970 Kelvin, depending on pressure. Carbon dioxide condenses at similar temperatures but can remain stable at slightly warmer conditions. For CO to dominate over water, you need either a carbon-rich formation environment, perhaps around a carbon star, rather than a sun-like star, or formation at extreme distances where both ices condense, but CO somehow became more abundant. Both scenarios are exotic compared to our solar system's history. The JWST observations also revealed the detailed shape of the CO emission bands, which provides information about temperature and velocity of the gas. The carbon dioxide was being released at velocities suggesting sublimation directly from the nucleus, not secondary production in the coma. This rules out some exotic chemical reactions converting other materials into CO. The carbon dioxide was actually present as ice in the nucleus, sublimating as the comet warmed. But here's where the chemistry becomes not just unusual but contradictory. Despite having much less water than typical comets, 3A Atlas showed strong water emission far from the Sun, out beyond 3.5 astronomical units, at distances where water ice shouldn't sublimate effectively. Observers described it as a fire hose of water release at distances where most comets show minimal activity. This is the opposite of what you'd expect from a carbon dioxide-dominated comet. Think about the physics. Water ice has a sublimation curve that depends on temperature. At 3.5 AU from the Sun, surface temperatures are too low for vigorous water sublimation. You might get slow, diffuse outgassing as solar radiation penetrates surface layers, but not the strong emissions 3I Atlas displayed. Carbon dioxide, being more volatile, can sublimate at those distances, and that's presumably what was driving the observed activity. But the water release was stronger than it should be. This suggests either unusual nucleus structure, perhaps layered ice with CO folds, ice overlying water ice, where CO folds sublimation creates fissures allowing water vapor to escape, or heating mechanisms beyond simple solar radiation. Neither explanation is satisfying. Layered structures require specific formation scenarios. Additional heating requires energy sources we haven't identified. The hydrogen cyanide detected in the spectra adds another layer of complexity. HCN forms in carbon-rich environments, consistent with the high CO4's abundance. But the amount detected relative to water exceeded typical cometary values. This reinforces the picture of a carbon-rich object, but raises questions about what kind of star system produces such chemistry. Carbon stars exist. Evolved stars that have dredged carbon from their cores to their surfaces through convection, creating carbon-rich atmospheres and circumstellar material. Could 3I Atlas have formed around such a star? Possibly, but that's yet another exotic scenario required to explain the data. What's frustrating from a scientific perspective is that each individual measurement has a potential natural explanation. High CO hive. Maybe it formed around a carbon star. Early water release? Maybe unusual nucleus structure. Strong HCN? Consistent with carbon-rich formation. But these explanations don't necessarily work together coherently. They're individual patches covering holes in our understanding, rather than a unified model that explains everything simultaneously. And we haven't even addressed how this chemistry connects to the nickel paradox discussed earlier, or the anti-solar tail structure, or the rotation anomalies we're about to explore. Each observation seems to require its own special explanation. At some point, special case becomes pattern of anomalies, and patterns demand broader explanations. In scientific literature, there's a principle called Occam's razor. The simplest explanation that accounts for all evidence is usually correct, but Occam's razor assumes you're choosing between explanations of comparable plausibility. When your simple explanation is formation around a carbon star with unusual metal enrichment and peculiar ice structure and exotic volatile retention, you're not really being simple anymore, you're stacking assumptions. And that's when alternative hypotheses start deserving serious consideration. The chemistry revealed by JWST tells us that 3I Atlas isn't just an interstellar visitor. It's a visitor from a planetary system environment profoundly different from our own. Whether that difference is natural variation within the galaxy's diversity or something more intentional remains an open question. But the data keeps pushing us toward acknowledging that this object doesn't fit our categories, doesn't match our expectations, and demands explanations we haven't yet fully articulated. While astronomers on Earth were puzzling over these chemical anomalies, spacecraft millions of kilometers away were racing against time to capture their own observations, knowing that this opportunity to study 3i Atlas from close range would never come again. And what those spacecraft revealed only deepened the mystery. October 3rd, 2025, marked a unique moment in astronomical history, the day when Comet 3i Atlas passed within 30 million kilometers of Mars, close enough for orbiting spacecraft to attempt detailed observations from a perspective impossible to achieve from Earth. This wasn't planned. When ExoMars Trace Gas Orbiter and Mars Express were launched years earlier, nobody knew an interstellar comet would eventually drift past Mars at observable range. But opportunity appeared, and engineers scrambled to take advantage of it. Spacecraft orbiting Mars aren't designed for deep space astrophotography. Their instruments are built to study Mars, its surface, atmosphere, magnetic environment. ExoMars TGO's color and stereo surface imaging system is optimized for photographing Martian terrain from orbit, resolving details as small as a few meters across. Mars Express's high-resolution stereo camera is designed similarly, intended to create topographic maps of Martian geography. Neither instrument is meant to photograph objects millions of kilometers away, but both spacecraft have pointed cameras. And where there are cameras, there's possibility. The challenge was immense. Comets are faint. Even when active and bright by astronomical standards, they're still vastly dimmer than planetary surfaces illuminated by direct sunlight. ExoMars TGO and Mars Express would be attempting to photograph an object roughly 50,000 times fainter than Mars itself, using instruments designed for a completely different purpose. It would be like using a microscope to photograph a distant mountain, technically possible if you're creative, but far outside the instrument's designed use case. Flight controllers had to reprogram pointing sequences, commanding the spacecraft to orient away from Mars toward specific coordinates in space. This requires precise timing. Spacecraft in orbit move constantly, completing circuits around Mars every few hours. The observation window, when 3i Atlas would be in the right position relative to the spacecraft's trajectory, lasted only days. Miss it, and the comet would recede back into deep space, never to be this close to human-built instruments again. On October 3rd, both spacecraft successfully captured images. The exposures were long, allowing sensors to accumulate enough photons to detect the faint comet. This introduces challenges. Spacecraft aren't perfectly stable during long exposures, so images can blur from slight pointing drift. Cosmic rays constantly strike detectors in space, creating bright spots that must be filtered out in processing. The star field behind the comet adds background light, requiring careful subtraction to isolate the comet's signal. Despite these difficulties, the images revealed structure, not with Hubble's clarity or Keck II's resolution, but enough to confirm asymmetric features in the coma, consistent with the anomalous jets detected from Earth. From Mars's vantage point, the geometry was different. The viewing angle changed how these structures projected against the sky, yet the fundamental strangeness remained visible even in these challenging observations. What makes the Mars spacecraft observations particularly valuable is their completely independent instrumentation. When you're trying to verify an unusual observation, the ideal situation is confirmation from a totally different instrument, designed and built by different teams, operating with different systematic errors. ExoMars TGO and Mars Express share no components with Keck II, Hubble, or Gemini South. They have different optics, different detectors, different image processing algorithms. Any artifacts or systematic biases in Earth-based observations wouldn't appear in Mars spacecraft data, and vice versa. The fact that consistent anomalies appear across all these diverse observations is powerful evidence that the features are real, not instrumental effects or processing artifacts. When one telescope shows something unusual, skepticism is warranted. When 5 different observing platforms, using different technologies, operated by different space agencies, all show consistent anomalies, skepticism becomes increasingly difficult to maintain. The ExoMars TGO observations had an additional component: spectrographic measurements attempting to detect gases in the coma. TGO carries instruments designed to search for trace gases in Mars's atmosphere, sensitive to molecules at parts per billion concentrations. These instruments can be used, with appropriate reconfiguration, to study cometary emissions. The data is still being analyzed as of October 2025, but preliminary results suggest detection of CO, possibly water vapor, consistent with ground-based observations, but providing independent verification. Mars Express, despite being older, launched in 2003, contributed valuable temporal coverage, while ExoMars TGO captured snapshots during closest approach. Mars Express monitored the comet over several orbital passes, watching how its appearance changed over hours. This temporal dimension helps distinguish between static features and dynamic activity. What they found was variability. The coma brightness and structure changed measurably over timescales of hours, suggesting active outgassing that varied as the nucleus rotated or as jets turned on and off. There's something profound about the fleeting nature of this opportunity. 3I Atlas is passing through our solar system once. It emerged from interstellar space, swung past the Sun, and will return to interstellar space, never to revisit our region of the galaxy within any conceivable human timescale. The Mars flyby on October 3rd represented a brief moment when human-built instruments happened to be positioned to observe from close range. Days later, the geometry had changed, the comet had moved on, and the opportunity evaporated. No mission can be launched to chase it. Spacecraft take years to build and launch. Even our fastest probes would take decades to catch an object already receding at interstellar velocities. The New Horizons spacecraft, which flew past Pluto and is currently humanity's farthest active probe, took 9 years to reach Pluto and is traveling at about 14 kilometers per second relative to the Sun. 3I Atlas is moving even faster, and in a different direction. We couldn't catch it if we tried. This creates urgency. Every observation matters, because observations are limited. Every spectrum, every image, every data point is potentially irreplaceable. When ExoMars TGO and Mars Express captured their images on October 3rd, they were gathering data that can never be replicated, information that will be analyzed and reanalyzed for years, as scientists attempt to extract every possible insight. The Mars observations also provided distance measurements, helping refine the comet's trajectory. Knowing the precise path through the solar system allows calculation of its origin, what direction it came from in interstellar space, which star systems it might have passed near during its millions of years' journey through the galaxy. This trajectory data, combined with composition measurements, might eventually point toward the comet's birthplace, offering clues about what kind of stellar environment produces such unusual chemistry. But trajectory alone doesn't explain the observed anomalies. It doesn't tell us why the comet has an anti-solar tail, why its nickel-to-iron ratio is wrong, why its carbon dioxide dominates over water. Those mysteries require understanding the comet's physical properties, its size, shape, rotation, surface structure. And here too, observations revealed puzzling features that defy simple explanation. As spacecraft imaged the comet from space and telescopes tracked it from Earth, photometric observations, measuring brightness variations over time, uncovered a rotation pattern that raises yet more questions about what 3I Atlas actually is and how it formed. Light curves don't lie. When you monitor an asteroid or comet's brightness over hours and days, you're watching shadows and reflections change as the object rotates. A spherical object shows constant brightness. An elongated object, tumbling through space, grows brighter and dimmer in a repeating pattern as different cross-sections face your telescope. The period of this brightness variation equals the rotation period. how long it takes the object to spin once on its axis. For 3I Atlas, photometric monitoring throughout August and September 2025 revealed a clear periodicity 16.16 hours. Every 16 hours and roughly 10 minutes, the brightness pattern repeated. This indicates either rotation, the nucleus spinning on its axis, or some other process operating with precise regularity. Given that rotation is the simplest explanation, and that most comets and asteroids do rotate with periods ranging from minutes to days, interpreting this as the spin period is reasonable. 16 hours is unremarkable for a comet, neither particularly fast nor unusually slow. 67 P/Churyumov-Gerasimenko, visited by Rosetta, rotates every 12.4 hours. Comet Hale-Bopp had a rotation period around 11.3 hours. So the period itself doesn't raise red flags. What's noteworthy is the precision of the periodicity and what it implies about the nucleus's structure. The amplitude of the light curve, the difference between brightest and dimmest phases, suggests the nucleus is elongated rather than spherical. A sphere rotating would show no brightness variation because every orientation presents the same cross-section. An elongated object, like a potato or football, presents different cross-sections as it tumbles, creating brightness variations. The observed amplitude for 3I Atlas suggests an axis ratio of perhaps 2:1 or 3:1, meaning the long axis is 2 to 3 times longer than the short axis. But here's where things become puzzling. The activity, the outgassing visible in images and spectra, doesn't correlate simply with rotation. If the nucleus had active regions on its surface, localized areas that release gas and dust, you'd expect activity to peak when those regions face the sun and diminish when they rotate into shadow. The rotation period should be visible in the activity level, with brightness and gas production varying systematically every 16.16 hours. Observations show activity variations. Yes, but they don't neatly align with the rotation period. There are variations on shorter timescales, hours, and longer trends over days that don't sync with the 16.16-hour cycle. This suggests either multiple active regions with different characteristics or activity driven by processes not directly tied to rotation and sunlight illumination, or a nucleus whose structure is more complex than a simple rotating potato. The coma structure added another layer of mystery. High-resolution images from Keck II and Gemini South showed that the dust and gas surrounding the nucleus weren't distributed symmetrically. Instead of a roughly spherical cloud, the coma displayed asymmetries, brighter on one side, extended structures that looked like fans or jets radiating from specific locations. This asymmetry persisted across multiple observations, even as the nucleus presumably rotated. For a rotating nucleus with localized jets, you'd expect the jet patterns to rotate with the nucleus, creating a spiral structure in the coma as material ejected from active regions follows curved paths, while the source rotates. We've seen this in other comets, beautiful spiral patterns traced by dust ejected from specific spots. 3I Atlas showed jets, yes, but their orientation relative to the sun didn't change as expected from simple rotation models. One interpretation, the nucleus is rotating, but its shape and mass distribution create complex dynamics. Many asteroids and comets rotate in complex ways, tumbling chaotically rather than spinning around a single stable axis. This non-principal axis rotation happens when an object isn't perfectly rigid, or when outgassing creates torques that push the spin axis around. It's complicated but natural. Another interpretation: the activity isn't primarily controlled by rotation. Perhaps subsurface reservoirs of volatile ices are rupturing as heat conducts inward from the surface, creating outbursts that don't correlate with rotation. Perhaps the anti-solar jet is driven by a mechanism unrelated to normal solar heating, operating independently of which part of the nucleus faces the sun. This interpretation opens doors to more exotic explanations. Throughout late September and early October 2025, Observers watched the comet's tail grow progressively more prominent. As 3I Atlas approached perihelion, its closest point to the Sun, which occurred on October 29th, activity increased substantially. This is expected. Closer distance means more solar radiation, higher surface temperatures, more vigorous sublimation. Every comet brightens and becomes more active as it nears the Sun. But the rate of brightening didn't follow standard models perfectly. Typically, comet brightness follows a power law related to distance. As distance decreases by a certain factor, brightness increases by a predictable amount based on how the comet responds to solar heating. For 3I Atlas, the brightening was steeper than typical, suggesting either increasing active area as more of the surface began outgassing, or non-linear response to solar heating, or perhaps fracturing of surface layers exposing fresh ice beneath. The tail structure evolved too. Early observations in July and August showed minimal tail development, mostly just the coma around the nucleus. By September, a faint tail appeared in long-exposure images. By October, multiple tail structures were visible. The anomalous sunward jet, a faint classical anti-solar tail barely visible in long exposures, and possible lateral features suggesting jets at angles not directly toward or away from the Sun. This complexity is unusual but not unprecedented. Comets can develop multiple tails as different materials respond differently to solar radiation pressure and solar wind. Dust and ions separate, creating distinct tails. Active regions at different latitudes on a rotating nucleus can create multiple jets that collectively form complex structures. But for 3I Atlas, the structures didn't fit neatly into these familiar patterns. The dominant feature was still that sunward jet, the impossible tail pointing the wrong direction. Photometric observations also attempted to detect rotation in the near-infrared, where thermal emission from the nucleus itself might be detectable. As different parts of the surface rotate into sunlight and heat up, then rotate into darkness and cool down, you'd expect a thermal light curve offset from the visible light curve. This thermal phase lag provides information about how quickly the surface responds to heating, which tells you about the material properties, whether the surface is bare ice or covered with dust or something else entirely. The thermal observations were challenging because 3I Atlas remained relatively faint even at its brightest. But preliminary data suggested a thermal lag consistent with a surface covered by some amount of insulating material, dust, perhaps, or refractory organics, rather than bare ice. This is typical for comets. But combined with the unusual chemistry and activity patterns, it adds one more data point to the growing collection of measurements that don't quite paint a coherent picture. The rotation period of 16.16 hours, the asymmetric coma, the activity variations that don't correlate simply with rotation, the evolving tail structure, each piece is a fragment of the puzzle. Individually, each might be explainable through known processes. Collectively, they suggest an object whose behavior is complex, possibly revealing a structure or composition we don't fully understand. And as observers documented these patterns, trying to fit them into models of cometary behavior, they couldn't escape the central question: what mechanism could produce the anti-solar tail, that feature pointing toward the Sun in violation of radiation pressure physics? The answer to that question might explain everything, or it might reveal that 3I Atlas is something entirely outside our experience. Radiation pressure is relentless. Every photon carries momentum, and when photons from the Sun strike dust grains or gas molecules in a comet's coma, they transfer that momentum, pushing material away from the Sun. This is why comet tails point away from the Sun, not because the comet is moving, but because the Sun's radiation actively shoves material outward. Solar wind, that stream of charged particles flowing from the Sun's corona at hundreds of kilometers per second, adds to this outward push. Together, radiation pressure and solar wind define cometary tail geometry. Tails point away. Always, except for 3I Atlas, where observations clearly show material streaming toward the Sun. Let's eliminate the easy explanations first. The most common cause of apparent sunward tails in solar system comets is geometry, viewing angle, creating an illusion. When a comet's orbit carries it across our line of sight, the dust tail, which curves due to orbital motion, can appear to point sunward from certain angles even though it's actually pointing away in three-dimensional space. This is called an anti-tail, a misleading name because it's not actually pointing toward the sun, it's just projected to appear that way from Earth's viewing angle. Orbital geometry doesn't explain 3I Atlas's feature. The comet's trajectory relative to Earth during August and September 2025 was such that geometric projection would create an anti-tail effect in a completely different direction than what was observed. The sunward jet appeared in a position that can't be explained by viewing angle. Multiple observation dates from different Earth positions all showed the feature in the same location relative to the comet and sun. This rules out geometric illusion. Could it be dust falling back toward the nucleus under the comet's own gravity? Cometary nuclei are small, with weak gravity. For 3I Atlas, assuming a nucleus diameter around 1–2 kilometers and typical cometary density, surface gravity would be roughly 1/1,000,000th of Earth's. Dust grains ejected from the surface at even modest speeds, a few meters per second, would escape this gravity easily. So while some dust might fall back, particularly large grains ejected at low speeds, this wouldn't create a coherent jet extending thousands of kilometers sunward. Gravity can't explain this. Electric fields offer a more intriguing possibility. Comets develop electric charges as solar ultraviolet radiation ionizes gas in the coma, stripping electrons and creating a plasma environment. In theory, charge separation could create electric fields strong enough to accelerate ions. If the nucleus developed a significant positive charge, and if ions in the coma had the right charge-to-mass ratio, electric acceleration might push material sunward against radiation pressure. But this requires specific conditions. The electric field must be strong, sustained voltages of thousands of volts across the coma. The ions must be heavy enough that radiation pressure doesn't dominate. And the geometry must channel ions specifically sunward rather than radially outward in all directions. Calculations suggest that while electric effects might contribute to anomalous velocities, creating a sustained jet visible across multiple observations would require electric fields stronger than typically measured in cometary environments. There's also the problem of what maintains such a field. Electric charges dissipate quickly in a partially ionized gas. Electrons and ions recombine, currents flow, and the system tends toward charge neutrality. Maintaining a strong electric field requires continuous charging, which usually means some asymmetric process generating more ions on one side than the other. Solar radiation comes from one direction, so it's unclear how that creates asymmetry leading to sunward acceleration rather than simple radial effects. Another hypothesis: interaction with the interstellar medium. Space isn't empty. Even between stars, there's low-density gas, mostly hydrogen, with traces of helium and heavier elements. When a comet, moving at interstellar velocities, plows through this medium, it creates a shock wave, compressing the interstellar gas ahead of it. Could this interaction somehow funnel material sunward? The problem is that 3I Atlas isn't moving at interstellar velocity anymore. By the time it reached Earth's neighborhood in August–September 2025, it had decelerated under the sun's gravity, moving at speeds comparable to solar system objects, tens of kilometers per second relative to the sun, not hundreds. Its interaction with the interstellar medium should be minimal, far too weak to create visible structures. Some researchers propose that the sunward feature might be gas rather than dust, and that gas dynamics could behave differently than dust. Gas molecules experience radiation pressure too, but they also have thermal velocities, random motion due to temperature. If gas is released from the nucleus with significant initial velocity toward the sun, perhaps due to subsurface pressure releasing through a vent, it might travel sunward for some distance before radiation pressure eventually decelerates and reverses its motion. This gas fountain model has precedent. Comets do release gas at supersonic speeds from active vents, but sustaining a sunward flow visible across thousands of kilometers requires enormous gas production rates and very specific vent geometry, and observations showed the feature persisting across multiple dates, implying sustained activity rather than a brief outburst. Continuous sunward gas release would need continuous driving pressure, which is hard to maintain over weeks unless something is continuously replenishing subsurface volatiles. Here's where we need to acknowledge something uncomfortable. Natural explanations for the antisolar tail require stacking special conditions, unusual electric fields, exotic gas dynamics, precisely oriented vents, sustained activity patterns that don't match rotation. Each individual component is physically possible, but their combination, all operating simultaneously, all aligned to produce the observed effect, begins to strain plausibility. This is where scientific honesty demands we acknowledge alternative frameworks. If natural processes struggle to explain the observations, we should at least consider whether the framework is wrong. What if the feature isn't naturally generated? What if it's a directed effect? A purposeful structure rather than an accidental one? Before dismissing that as science fiction, consider what such a hypothesis would predict. An artificial mechanism producing a sunward jet would likely show regularity, sustained operation, and possibly correlation with the rotation period if it's mounted on or within the nucleus. It would consume energy, so we might expect heat signatures or unusual activity patterns. It would have a purpose, perhaps attitude control, trajectory adjustment, or some function we haven't imagined. Interestingly, some of these predictions align with observations. The jet does show sustained operation across multiple observation epochs. There are rotation-related variations in activity, though not perfect correlation. The heat budget of the comet, energy input from solar radiation versus energy output via sublimation, hasn't been perfectly balanced in all models. Some analyses suggest slightly more activity than solar heating alone would predict, implying either highly efficient energy conversion or additional heat sources. None of this proves artificiality, but it illustrates that dismissing the hypothesis without examining evidence is just as unscientific as accepting it without evidence. Right now we have observations that challenge natural explanations and that happen to be consistent with some predictions of artificial mechanisms. The scientific approach is to gather more data, refine models, and let evidence guide conclusions rather than letting assumptions dictate which hypotheses we're willing to consider. One particularly intriguing detail: the lack of a prominent dust tail in white light observations. Radiation pressure acts strongly on small dust grains, which have high surface area to mass ratios. If 3I Atlas is releasing dust as normal comets do, that dust should be blown away from the sun, creating a visible tail even if faint. The relative absence of such a tail, while the sunward feature is prominent, suggests the sunward feature might be gas-dominated or composed of different material than typical cometary dust, or generated by a process that doesn't release dust in the usual way. Gas-dominated emissions could come from subsurface reservoirs of volatiles venting through specific pathways. This happens in solar system comets. Comet Hartley II, visited by NASA's Deep Impact spacecraft in 2010, showed jets of CO ice chunks and water vapor erupting from specific locations. But again, those jets dispersed radially outward, not sunward. To produce sunward flow requires either extreme initial velocities or some force besides radiation pressure. We're left with an unresolved puzzle. Multiple hypotheses exist, none entirely satisfying. Natural mechanisms require special conditions. Artificial mechanisms require accepting that an interstellar visitor might be more than just a cosmic iceberg. As of October 2025, the data doesn't definitively favor either framework. What it does definitively show is that 3I Atlas doesn't behave as our models predict, and that explaining its behavior demands either significant revision of those models or consideration of entirely new categories of explanation. And as we ponder these mysteries, we can't help but look back at the previous interstellar visitors and ask whether they too challenged our assumptions in ways we didn't fully appreciate at the time, revealing a pattern that might be even more significant than any single anomaly. 3 visitors, 3 anomalies, 3 times our assumptions shattered. Oumuamua arrived first, in October 2017, detected by Pan-STARRS telescope as it was already leaving the solar system. Its trajectory immediately marked it as interstellar, entering from outside, swinging past the sun, departing into deep space. Initial observations suggested an asteroid, reddish in color, elongated based on brightness variations. Fascinating, but perhaps not revolutionary. Then came the acceleration. As Oumuamua receded from the sun, tracking measurements showed it was accelerating slightly beyond what gravitational forces predicted. For a comet, this wouldn't be surprising. Outgassing creates rocket thrust, pushing the comet slightly off a purely gravitational trajectory. Except, Oumuamua showed no visible coma, no tail, no spectroscopic evidence of outgassing. It behaved like an asteroid but accelerated like a comet. The scientific community proposed explanations. Maybe it released gas at rates too low to detect but sufficient for acceleration. Maybe it was composed of pure hydrogen ice, which would sublimate invisibly. Maybe solar radiation pressure acted on its elongated shape, creating acceleration. Each explanation had problems, requiring specific conditions or exotic compositions. The debate continues. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second confirmed interstellar visitor, 2I/Borisov. Unlike Oumuamua, this one behaved exactly like a comet from the start. It had a visible coma, showed normal outgassing, displayed the expected water and carbon monoxide emissions. Spectroscopy revealed chemistry similar to solar system comets. Its trajectory was clearly interstellar, but its behavior was familiar. As 2I/Borisov suggested that maybe Oumuamua was the oddball, and most interstellar objects would be recognizable. Then came 3I Atlas, discovered in January 2025 by the Asteroid Terrestrial Impact Last Alert System ATLAS. It initially seemed like it might follow 2I/Borisov's template, an interstellar comet, unusual for its origin but normal in behavior. Early observations showed outgassing, a developing coma, the hallmarks of cometary activity. But as monitoring continued through spring and summer 2025, the anomalies accumulated, the anti-solar tail, the nickel paradox, the backwards chemistry with carbon dioxide dominating over water, the rotation mysteries. Everything we've discussed in previous sections, 3 interstellar objects, 3 different behaviors. One showed acceleration without outgassing. One showed perfectly normal cometary activity. One shows outgassing but with impossible geometry and chemistry. The pattern emerging is unsettling. Interstellar visitors consistently break our rules, just in different ways each time. This challenges a fundamental assumption. We thought interstellar objects would resemble solar system objects, because the physics of planetary system formation should be universal. Dust and gas collapse into stars, forming surrounding disks where planets and comets accrete. The chemistry varies based on stellar type and disk temperature, but the basic processes are the same everywhere. Comets from other stars should look like our comets, with variations in composition reflecting different formation environments, but not fundamentally different physics. Yet here we are with 3 visitors, and not one fits neatly into our categories. Oumuamua accelerates mysteriously. 2I/Borisov seems normal, but might be the exception. 3I Atlas displays chemistry and behavior that strain natural explanations. If this is our galaxy's diversity, then our solar system appears to be the outlier, not the norm. Consider the statistics. How many interstellar objects pass through the solar system undetected? Our detection capability is limited. We only spot objects bright enough, close enough, and during clear weather when telescopes happen to be pointing the right direction. Estimates suggest dozens to hundreds of interstellar objects traverse the inner solar system annually. but we've only detected 3. Those 3 might be the tip of the iceberg, or they might be statistical flukes, the only ones large enough and close enough to see. If they're representative of galactic diversity, then the galaxy is stranger than we imagined. If they're outliers, we need to explain why we happen to detect 3 unusual objects rather than any ordinary ones. Neither option is comforting. Either the universe is consistently weird, or our detection methods are biased toward weirdness. There's also a pattern in what these objects are teaching us. Beyond just things are strange, each visitor challenged a different aspect of our understanding. Oumuamua challenged our assumptions about cometary activity and what counts as outgassing. 2I/Borisov reinforced those assumptions, showing that at least some interstellar comets behave normally. 3I Atlas is now challenging our understanding of chemistry, tail formation, and what counts as natural versus artificial. It's as if each object is probing a different weakness in our models, revealing gaps we didn't know existed. And perhaps that's the real lesson. Our models are built on observations of solar system objects, thousands of comets and asteroids, but all formed in the same stellar environment, all composed of variations on the same initial chemistry. When we encounter objects from truly different origins, our models stumble because they're extrapolating beyond their foundation. Galactic chemistry varies enormously. Stars form in different types of molecular clouds with varying carbon to oxygen ratios, different abundances of metals, different isotopic signatures. A comet forming around a carbon-rich star would have different chemistry than one forming around an oxygen-rich star. A comet forming in the outer regions of a massive star's disk, where temperatures and radiation environments differ drastically from our solar system's history, might preserve exotic ices we've never encountered. Interstellar exposure also matters. These objects have been traveling through the galaxy for potentially millions or hundreds of millions of years since ejection from their parent systems. Cosmic rays constantly bombard them, slowly altering surface chemistry, creating radiation-processed materials. Interstellar dust impacts erode surfaces. Magnetic fields might induce electrical effects. By the time an interstellar object reaches us, it's not just a pristine sample of its formation environment. It's been weathered by the galaxy itself. But even accounting for all this natural variation, the specific anomalies of 3I Atlas strain explanations. The sunward tail isn't just unusual chemistry. The nickel-to-iron ratio isn't just cosmic ray exposure. The carbon dioxide dominance isn't just formation around a different star type. Each might be explainable individually, but their combination paints a picture that doesn't fit any known natural environment. And this brings us to the uncomfortable question hovering over all these discussions. If natural processes struggle to explain 3I Atlas, and if we're being scientifically honest about examining all hypotheses that fit the data, we need to ask, could this object or aspects of it be artificial? Could we be observing technology rather than geology, engineering rather than natural processes, design rather than accretion? I'm not claiming that's the answer, but I am claiming that dismissing the question without examining evidence is ideology, not science. Science follows data, and the data from 3I Atlas, combined with the pattern of anomalies across all 3 interstellar visitors, suggests that something is happening that our current framework doesn't accommodate. Whether that something is exotic natural processes from star systems vastly different from our own, or whether it's something more intentional, remains to be determined. What we can say with confidence is that interstellar objects are not just interesting for their exotic origins. They're important because they're revealing the limitations of our understanding, forcing us to confront assumptions we didn't know we were making, and pushing science toward broader frameworks that might eventually explain not just these 3 visitors, but the diversity we'll encounter as we detect more in coming decades. Improved telescopes are coming online. The Vera-C Rubin Observatory, beginning operations in 2025, will detect thousands of asteroids and comets nightly, likely spotting multiple interstellar visitors per year. In a decade, we might have dozens of interstellar detections, enough to understand whether Oumuamua, 2I/Borisov, and 3I Atlas are representative or exceptional. But right now, in October 2025, we have 3 data points, and all 3 are puzzling in different ways. The education these visitors provide is uncomfortable because it reveals how much we don't know. We thought we understood comets. We thought planetary formation was universal. We thought physics was physics, regardless of where you formed in the galaxy. These visitors are teaching us humility, showing us that our corner of the solar system might be calmer, more ordinary, less representative than we assumed. And as 3I Atlas heads toward perihelion, reaching its closest approach to the Sun on October 29th, 2025, we're about to learn even more, potentially including revelations we're not prepared to accept. October 29th, 2025. Perihelion. The moment 3I Atlas reaches its closest approach to the Sun, roughly 0.39 astronomical units, inside Earth's orbit, about the same distance as Mercury's average orbital radius. This is when comets become most active. Solar radiation intensity peaks. Surface temperatures soar. Subsurface ices buried beneath dust mantles finally reach sublimation temperatures. If 3I Atlas has secrets hidden beneath its surface, perihelion is when those secrets might reveal themselves. Observatories worldwide have coordinated observing campaigns. Hubble, James Webb, Keck, Gemini, the Very Large Telescope in Chile, radio telescopes searching for molecular emissions, all are scheduled to observe during this critical period. The goal is comprehensive coverage, optical imaging, infrared spectroscopy, ultraviolet observations, radio wavelengths, all capturing the comet at peak activity. If ever there was a moment to gather definitive data, this is it. But as of this script's writing in mid-October 2025, we don't yet know what those observations will reveal. We're in the strange position of discussing a mystery that's actively unfolding in real time. This isn't ancient history or distant events we're reconstructing from archaeological evidence. This is happening now. As you watch this, astronomers might be analyzing fresh data from perihelion observations, possibly finding answers, possibly finding deeper questions. So let's talk about what those answers might look like and what they would mean. If natural processes explain everything, if the anomalies resolve through some combination of exotic formation environment, unusual nuclear structure, and chemical processes we haven't fully modeled, then what we're witnessing is an expansion of our understanding. We'd learn that comets can form with carbon dioxide-dominated compositions, that metal-carbonyl chemistry can occur in certain stellar environments, that nucleus geometry can produce unexpected outgassing patterns. This would be fascinating science, worthy of publication in Nature or Science, groundbreaking for cometary physics. It would tell us the galaxy's diversity exceeds what our solar system prepared us for. This natural explanation would fit into existing scientific frameworks. It wouldn't require rewriting physics textbooks or questioning fundamental principles. It would add complexity and nuance, but not revolution. And honestly, this is the outcome most scientists expect, because we're trained to exhaust natural explanations before invoking extraordinary hypotheses. But what if natural explanations continue to strain? What if perihelion observations reveal activity levels that exceed solar heating predictions, or show the anti-solar jet strengthening in ways radiation models can't accommodate, or detect chemical signatures incompatible with any known stellar formation environment? What if the pattern of anomalies becomes impossible to explain through stacked special conditions? Then we face a choice. We can continue proposing increasingly exotic natural scenarios, adding layers of complexity to force observations into a natural framework. Or we can acknowledge that our framework might be incomplete, that the category of natural comet might not accommodate what we're observing, that 3I Atlas might represent something entirely outside our established classifications. Let me be clear about what I'm suggesting. I'm not claiming 3I Atlas is an alien spacecraft. I'm not saying it's artificial. What I am saying is that the data as of October 2025 is consistent with unusual natural processes and also consistent with some artificial components or intervention. Both possibilities remain on the table until evidence definitively eliminates one. Scientific history offers cautionary tales in both directions. The discovery of pulsars in 1967 initially seemed so regular, so precise, that they were briefly considered possible alien beacons, even nicknamed LGM for little green men. Further observations revealed them as neutron stars with natural explanations. But if astronomers had dismissed the artificial hypothesis without investigation, had refused to even consider it because it seemed too extraordinary, they'd have failed in their responsibility to examine all explanations consistent with data. Conversely, the face on Mars photographed by Viking 1 in 1976 inspired speculation about artificial structures. Higher resolution images decades later revealed it as a natural mesa whose face-like appearance was pareidolia, human tendency to see patterns. Here, the artificial hypothesis was investigated and eliminated by evidence, as it should be. For 3i Atlas, we're at the investigation stage. The artificial hypothesis hasn't been proven, but it also hasn't been definitively eliminated. The natural hypothesis faces challenges, but hasn't been ruled out. More data will likely clarify which framework explains observations more successfully. But refusing to examine one hypothesis simply because it makes us uncomfortable would be a failure of scientific integrity. Consider what signs might distinguish artificial from natural. Artificial structures might show geometric regularity, sharp boundaries between different materials, isotopic ratios inconsistent with natural fractionation, thermal signatures indicating active power generation, trajectory adjustments unaccounted for by outgassing, signals or emissions with structured patterns. None of these have been definitively detected in 3i Atlas as of October 2025, but perihelion observations might reveal some. Conversely, natural comets show irregular shapes, chemical gradients following temperature profiles of the formation disk, isotopic ratios matching stellar nucleosynthesis products, thermal emissions consistent with solar heating and sublimation, trajectories following gravitational and outgassing forces, emissions correlated with molecular fluorescence. 3i Atlas shows some of these characteristics but not others, leaving its classification ambiguous. There's also the question of purpose. If 3i Atlas includes artificial components, what would they accomplish? Interstellar probes might be designed for observation, for sample collection, for trajectory adjustment, or purposes we haven't imagined. The anti-solar jet could be a propulsion system. The unusual chemistry could be fuel or construction material. The rotation period could indicate internal gyroscopes or attitude control. All speculation, yes, but speculation grounded in engineering logic rather than fantasy. What strikes me most about this situation is how it parallels historical moments when humanity confronted evidence that our position in the universe wasn't what we assumed. Copernicus realized Earth orbits the Sun, not the reverse. Harlow Shapley realized our Sun isn't at the galaxy's center. Edwin Hubble realized our galaxy is one among billions. Each revelation was initially controversial. Each challenged established frameworks. Each ultimately expanded our cosmic perspective. If 3i Atlas proves to be an unusual natural object, we learn that comets are more diverse than we knew. If it proves to have artificial aspects, we learn we're not alone in using interstellar space, that other intelligences have developed technology, that the galaxy is populated with explorers or travelers or scientists from civilizations beyond our own. Either way, our perspective expands. I realize this discussion might seem premature. We don't yet have perihelion results as of mid-October 2025. But consider why this video exists now rather than waiting for complete data. Because this is a moment to witness science in action, to see how discovery unfolds, to understand that major revelations don't arrive fully formed, but emerge gradually from accumulated observations. You're watching history potentially being written. By the time you see this video, perihelion might have passed. New data might be public. If so, I encourage you to look up the latest findings, read the press releases, examine the new images, follow this story as it develops, because regardless of the ultimate explanation, 3i Atlas represents the kind of mystery that makes science thrilling, a genuine unknown observable in real time, accessible to scrutiny, yielding conclusions based on evidence rather than speculation. For those of you who followed this channel because we explore mysteries others ignore, because we value evidence over narrative, because we're willing to ask uncomfortable questions when data demands it, 3i Atlas is exactly the kind of story we exist to cover. Not sensationalizing, not jumping to conclusions, but also not dismissing possibilities, simply because they challenge our assumptions. The revelation we might not be ready for isn't necessarily that 3i Atlas is artificial. It's that the universe is stranger than our models predicted, that our solar system might be atypical, that the rules we derive from local observations don't universally apply, and that every answer reveals deeper questions. Whether this comet is nature's exotic creation or something more intentional, it's rewriting our understanding of what interstellar visitors can be. I'll be watching the perihelion observations as closely as any of you. I'll be reading the papers, examining the data, updating my understanding as evidence accumulates. That's what honest inquiry demands. And when results are published, when we have clearer answers about what 3i Atlas actually is, I'll cover those findings here, following the evidence wherever it leads. In the meantime, if these mysteries pull at you the way they pull at me, if you value seeing through official narratives to examine raw data, if you're willing to entertain possibilities that don't fit comfortable frameworks, then subscribe to this channel and join this investigation. Because 3i Atlas is just one object. More interstellar visitors are coming. The Vera C. Rubin Observatory will find them, and each one will teach us something about the galaxy's diversity, about our place in the cosmos, about what's possible in this vast universe we're only beginning to explore. Comment below with your location, your thoughts on these observations, your predictions for what perihelion data will reveal. This isn't just my investigation, it's ours, collectively trying to make sense of evidence that challenges everything we thought we knew about comets. 3i Atlas, whatever it ultimately proves to be, represents a threshold moment. The moment when we stopped assuming interstellar visitors would be familiar, when we acknowledged that objects from beyond might play by different rules, when we became open to possibilities our theories hadn't predicted. And that openness, that willingness to follow evidence into uncharted territory, is what separates genuine inquiry from comfortable mythology. The universe is speaking. 3i Atlas is one of its messengers. The question isn't whether we're ready for its revelation. The question is whether we're brave enough to listen.